In this video, we are going to discuss angular momentum. Angular momentum is calculated by taking the lever arm distance, or radius, crossed with our linear momentum. So we're adding in that radial concept very similar to how we did with torque, where torque became R cross F. Now we're going to say angular momentum is R cross P. Now, remember, we can also replace momentum with mass times velocity. Remember, velocity is the vector. Now, let's focus in on one particle. So when we're dealing with one particle, and let's assume that that one particle is part of a rotating disk. So it's rotating about the center. So that we have r be some radial distance, and the velocity points this way tangent, so that r and v are perpendicular to each other. So that when we take the cross product, we can just collapse it down into a multiplication because the r and the v are perpendicular to each other already. Remember, we can replace velocity with the r times omega. So I can rewrite this as mass times r squared times the angular velocity. So if we want to find the angular momentum of the entire object, of course we need to sum over all particles, and that just becomes mass of each particle times its radius squared. So we're going to sum over all particles times the angular velocity, because the angular velocity is the same for the entire object. And this should look familiar here. This is essentially moment of inertia. So this is another way of calculating the angular momentum of the object. And unfortunately, just similar to regular momentum, angular momentum does not get any special units, so our units are going to turn out to be very long. They're kilogram meters squared per second. Alright, so now we want to talk about conservation of angular momentum. So we need to figure out the conditions under which angular momentum would be conserved. So we're going to start with our equation for angular momentum. And I'm going to take the derivative in terms of time to both sides. So as long as we do it to the both sides, it's a legal move. Alright, so I'm just going to recopy my left side, and my right side we need to use a product rule. So we're going to do the derivative of the first times the second plus the first times the derivative of the second. And remember, it's not really times we're doing here, they're still cross products. Alright, so let's do a little bit of reduction. We're going to keep this over here on the left the same. dr dt is velocity. And I can pull the mass out front because it's a constant, and dv dt is acceleration. Alright, so let's keep reducing. Alright, so remember, mass is not a vector. So we're looking at velocity cross velocity, and since it's the same vector, they're on top of each other, which means that their cross product would be 0, because they're not perpendicular, they're parallel to each other. So this term is going to go to 0. Alright, so let's look at our second term. That is going to be r cross, and mass times acceleration is force, so F. So what we're saying here is that the angular momentum is going to change. Remember, R cross F is torque. So if you apply a torque, then the angular momentum changes. If you do not apply a torque, then the angular momentum is conserved. And so when we say angular momentum is conserved, I'm going to go to our other equation for angular momentum. Now it's a little bit different than linear momentum. In linear momentum, we focused on the mass staying the same, just the velocity changing. So as we transfer momentum from one object to the other, the velocities of the two objects changed. Here with angular momentum, you're still getting angular velocity changing, but we're doing that not through a collision, but by changing the distribution of mass in the system. So this is why when you watch ice skating, you have your arms stretched out initially, and then the ice skater would tuck their arms in and start spinning faster. Because by tucking their arms in, the moment of inertia decreases, which allows the angular velocity to increase. So, as I said previously, we're getting a change in angular velocity not through a collision, but by a change in the distribution of mass in the system.